Hello everyone, I'm Paul and today we're solving problem 2787, ways to express an integer as sum of powers. This is a tricky medium one, so next I will show you how to solve this recursively and then iteratively. So let's start. We're given two positive integers n and x, and here is our job. We need to return the number of ways n can be expressed as the sum of the x power of unique positive integers. So for example, if n is 160 and x is 3, one way to express n is 2 to the power of 3 plus 3 to the power of 3 plus 5 to the power of 3. For example, if n is 10 and x is 2, we can express n as 3 to the power of 2 plus 1 to the power of 2. This is 10. And this happens to be the only way in which we can express 10 as the sum of the second power of unique integers. So given that there's only one way, the result in this case is 1. So this sounds tricky, honestly. Maybe you need to read this a few times, and we see a pattern here. We know that x is the exponent that we are using for this input. So we can try every possible base and check how many sets do we have that sum n, meaning 10 in this case. So we have different elements we can try here. We have 1 to the power of 2, 2 to the power of 2, 3 to the power of 2, and this is it. We can't try 4 to the power of 2 because this is 16. And 16 is greater than 10, so this is not valid. We can try these three elements. Now for each of these we have two choices. We can take or not take this, then we can take or not take this, then we can take or not take this. And we can keep track of the sum at each of these scenarios, and whenever this sum is equal to n, we know we found a valid set, so we can add 1 to the result. And whenever we keep track of previous results, we are using dynamic programming. So now I will show you how this works. First, let's start with the recursive approach. So this is the initial state. First we have n here, n is 10, remember this, and we are trying to reach 0. We know that if we reach 0, this means we found a valid set. So, just to be clear, the first value is n, and the second value is the current element. So we are first trying the first element. And here we have two choices. We can take this element or not take the element. And remember that x is 2 in this example. So if we decide to take this element, now we need to subtract this to the power of 2 from this. So we do 10 minus 1 to the power of 2, and this is 9. So the first value is 9, the second value is the next element, meaning 2. If we decide to not take this element, the current sum will be the same, meaning 10. And now we are at the second element. And here we can take 2, and if we take 2, we need to do 9 minus 2 to the power of x. 2 to the power of 2 is 4. So 9 minus 4 is 5. So the current value right now is 5, and now we are at the third element. And if we decide to not take these 2, the current value is 9, and now we are at 3. Similarly, here we can decide to take these 2, so we do 10 minus 2 to the power of 2, and this is 6. So here we have 6, and the next element is 3. And if we decide to not take these 2, we have the same 10. This 10 is this 10. And the next value is 3. And finally here we can take 3, so we have 5 minus 3 to the power of 2. And this is minus 4. And given that this is negative, we need to return 0. Because this means that 1 square plus 2 square plus 3 square is greater than n. So we need to return 0 in this case. If we don't take this, the state would be 5 and the next element meaning 4. And next we know that 4 square is greater than n, so this will also return 0. If we take this 3, the state will be 9 minus 3 square, and this is exactly 0. So now we can add 1 to the result. And what this means is 1 square plus 3 square is exactly n, which is 10. So this is our unique set, that's why this is 0, and that's why we add 1 to our result here. If we don't take this, the state is 9, 4, and we know that 4 times 4 is greater than n, so this returns 0. Now we are here. If we take 3, this will be 6 minus 3 square, and this is minus 3. And given that this is smaller than 0, we return 0. If we don't take 3, this is still 6. The next element is 4. We know that 4 times 4 is greater than n, so we return 0. If here we decide to take 3, the state would be 10 minus 3 square, and this is 1. And we know that 4 times 4 is greater than n, so here we return 0 also. And if we don't take 3, we keep 10, and the next element is 4. And here we also need to return 0. So we are trying every possible scenario, and whenever we find a valid set, we add 1 to the result. So finally we return this. Time and space complexity here will be roughly big O of n square. So now let's go with the code, and hopefully you will get the idea. First we say the mod value is 10 to the power of 9 plus 7. And now we are building our dp function. This takes an accumulated value and a number for the current element. We'll call this I. First we have the base cases. First, if accumulated is 0, this means we found a valid set, so we return 1. Now if accumulated is smaller than 0, we return 0 right away. Now the current power is I to the power of x modded by the required value. And here we have another base case. If current is greater than accumulated, we return 0. Now with this we can get the result, so this is initially 0, and we need to add the scenario in which we take the current value. So this is dp with accumulated minus current, and the next element is I plus 1. So this is scenario in which we take the current element. And we need to add the scenario in which we don't take the current element. This is dp with the same accumulated value and I plus 1. And just to be clear, this is not take. So now we can say result modulo equal the required value. And finally we return the result. And down here we can return a call to dp with n and the first element meaning number 1. And we need to cache this entire thing. So here we add the word cache. So this is it for the code. Now let's submit this and see if it works. So as you can see, this works, but we have a way to make this more efficient. So next I will show you the iterative approach. Now let's say we have this TP grid of size n plus 1 times n plus 1. Remember, in our example n is 10 and we need to include 10 in the grid, that's why we do this. And every value in this grid represents the number of ways in which we can sum the number corresponding to the current column, taking rows from 0 to the current row. So in this case from 0 to 3. And we are taking each of these rows to the power of x. So let's see what this means. First we are here. And the question is, how many possible ways do we have to get a sum of 0 with the elements we have seen so far? We have only seen 0, and 0 to the power of x is 0. So this is the only way in which we can get this sum. And given that there's only one way to get this sum, we put a 1 here. So now we are working with this row, meaning the current power is 1 to the power of x, and this is 1. So now we are here, and remember we have two choices. We can take the current element or not take the current element. Let's say we don't take this one here. In this case we need to use the previous result, meaning this one. So we use 1 here. Now here we can't take 1 because we are looking for numbers to get the sum of 0. And there's no way to get 1 to the power of 2 and get a sum of 0. So the only choice here is this, not take the current value. So we put another 1 here. So now we are here, and if we decide to not take 1 in this case, well, the result is 0. And for this scenario we need to take the previous result at the current index 1 minus the current power 1, and this is 0. So we are adding this here. So this is the number of ways to make the current column minus power without the current element, and then we add the power for the current element. That's why we need to add this here. So in this scenario in which we take the current element, right now we are here, the result is 1. And as you can see, 1 to the power of 2 is 1. And this is the only way to get 1. So now let's say we are here. If we decide to not take this element, we get the previous result. So this scenario is 0. And this scenario is the result for the previous element at the current column minus the current power. And 2 minus 1 is 1. So we look here and we have a 0, meaning the result for this scenario is also 0. So we have a 0 in both scenarios. And this makes sense because there's no way to get a 2 with only 0 and 1. So here we have a 0, and similarly this entire row will be 0. So now we are here and the current power is 2 to the power of 2, and this is 4. So we are working with this element, and remember we start here and we have two choices. We can take or not take this. If we don't take this, we look at the previous result, so we put a 1 here. And we can't take this element because we can never get a sum of 0 with 2 to the power of 2. So here we put a 1. Now here we can never get a sum of 1 by taking this element, so we can only not take the element. This means we can use this value. So we put a 1 here. So I think now you can see this is 0 and this is 0, and now let's say we are here and the current power is 4, meaning we can take the current element at this point. And if we take the current element, we go to the previous result and we do 4 minus the current power, meaning 4, this is 0. We put a 1 here. Now we are here, and if we don't take the current element, we have this value, meaning 0. And if we take the current element, we go to the previous result at the current column minus the current power. And what this means, for example, is we only have one way to get the sum of 5 with these elements. The only valid set here is 2 to the power of 2 plus 1 to the power of 2. And this is 5. The remaining elements here will be all 0, so we can continue with this element. So now we are here. If we don't take this element, the result is the previous result, so it's 1, and we can't take the current element to form a sum of 0. So we continue. Now we are here. If we don't take the current element, this is the result, meaning 1, and we can't take the current element because this sum is smaller than 3 to the power of 2. So actually, as you can see, we can never take this element until we reach this column. So this is the point in which we can start taking this element. And meanwhile, the result every time will be the result corresponding to the upper row. And now we are here, and if we don't take the current element, the result is this, meaning 0. And if we take the current element, the result is the previous row at the current column minus the current power, meaning this. And 1 plus 0 is 1, so here we put a 1. Now we are here, and we need to get a sum of 10. If we don't take this, the result is the result for the previous element, so this is 0. And if we take this, the result is the result for the previous row at the current column minus power, so it's this. 1 plus 0 is 1, so we add 1 here. The next element is 4 to the power of 2, and this is greater than 10, so we can end this loop here. And finally we can return this cell, which represents the number of different sets we can form with these elements, which have a sum equal to 10. So we return 1. Time and space complexity for this approach will be roughly big O of n squared. So now let's go with the code, and hopefully you will get the idea. First we say the mod value is 10 to the power of 9 plus 7. The DP grid is initially an array with, we are using this for columns, array with 0 times n plus 1, and for rows we use for every value in range n plus 1. And the only value that's not 0 initially is dp00. This is 1. Now we are using a variable maxi to keep track of the last valid row, meaning the last row in which the power was smaller or equal to n. Because remember, otherwise we need to break the loop. So this is 0, and for I in range from 1 to n plus 1, power is I to the power of x, and if at any point power is greater than n, we break the loop. Else we say the max I, meaning the maximum valid row, is the current row, so this is I. And now we can say for Shay in range n plus 1, we are iterating columns here. First we have the scenario in which we don't take the current element, so dpi Shay is dp I minus 1 Shay. And just to be clear, this is not take. Now, if the current column is greater or equal to power, we can take the current element. And this means we can do dpi Shay equals dpi Shay plus dpi minus 1 Shay minus power, and we need to mod this by the required value. And finally we can return dp max I n. So this is it for the code. Now let's submit this and see if it works. As you can see, this works and it's efficient. Time and space complexity here is big O of n squared, and we can make this even more efficient. We can use the exact same logic and use a 1D array here. So we can say this is now an array with 0 times n plus 1, and dp at 0 is 1. We can forget about this. For I in range from 1 to n plus 1, the current power is this. If power is greater than n, we break. We forget about this. And we can iterate this in reverse to avoid double counting. So we say for j in range from n included to power minus 1 in steps of minus 1. And here we can just say dp at j equals dp at j plus dp at j minus power, modded by the required value. And finally we can return dp at n. So this is how we can transform the 2D array into a 1D array. Now let's submit this and see if it works. As you can see, this works and it's very efficient. Time complexity here is still big O of n squared, but space complexity is big O of n. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.